Hey, Jerry Pal listeners, we're about to celebrate our 100th episode. Help us out and call 929-JERRY-PAL to tell us one thing you've learned or loved from the podcast in 15 seconds or less. Your message might make it on air. Again, that's 929-437-4725.
Welcome to the Jerry Pal podcast. This is Eric Guadera.
This is Alex Smith.
And Alex, we have someone in our studio audience, our office studio.
We have John Newman, who is a geriatrician and geroscientist.
A gero what?
A geroscientist.
A gero what?
A geroscientist who is held a joint appointment between UCSF and the Buck Institute for Aging Research. Welcome to the Jerry Pal podcast, John.
Thanks, guys. Thanks, Alex. Thanks, Eric.
I'm really interested to figure out what a geroscientist is, but before we do that, can we have a little song request for Alex?
Yeah, what should we sing about? Do you know a little song called Who Wants to Live Forever?
More Queen.
More, you can never get enough Queen.
Maybe our audience can. There's no time for us. There's no place for us. What is this thing that builds our dreams, yet slips away from us?
Telomeres.
Who wants to live forever? Who wants to live forever? Ooh.
John Newman does, right? John Newman wants all of us to live forever. At least that's why I am currently, those who are watching this on YouTube can see I am getting fresh stem cells from my baby farm that I get infused every day so I can live forever.
We're transfusing you as we speak.
As we speak.
As we speak.
Yeah, I give John hefty amounts of money for those baby transfusions.
Hey, that's the deal just for you, Eric. Don't go advertising me.
So, John, geroscience, what is this field, and is it about living forever?
It is not about living forever. It's about living healthier, longer, and staying independent. So what is geroscience?
I have no idea.
I don't know.
I thought I was here so you guys would tell me.
Old. Ben and Jerry's.
Aging science.
Aging science.
Aging science with a flavor of people.
So what is the difference between you and Alex? You're both researchers. Is Alex a geroscientist?
Well, geroscience is a made-up word which was coined for a new field and a whole new idea, which is now reality, which is going to sound a little crazy. Taking what we know about the biological mechanisms that drive aging, the biology of aging, and not only understanding that, which itself sounds a little crazy, but actually turning that into therapies to help to treat or prevent disease or help to improve the lives, especially of older adults. So geroscience is the idea of translational geriatrics, taking what we know about the basic science of the processes that drive aging and turning it into therapies and helping to improve people's lives.
The processes that, okay, so as I age, I'm just going to simplify this in my head. As I age, I start developing some chronic medical conditions. They start building up. I have more and more medical conditions. If only like I can just focus on making sure I don't develop those or I treat those well, like diabetes, COPD, would I prevent aging? Is that the goal here?
Well, what's the common, one place this comes from is what's that common underlying factor that's putting you at risk for COPD and for diabetes and for Alzheimer's disease and for cardiovascular disease and for strokes and for osteoarthritis and osteoporosis and for almost everything that we treat.
Nacho cheese Doritos.
That's a big one. That's a big one.
But there's more.
But what's the common denominator for all of those? We call these age-related chronic conditions or age-related diseases.
Yeah.
Because they're all driven by aging. And the key thing is that's not an accident, or it's not just like a probability thing, or it's not just time passing. But it's actually the biological mechanisms that change in our bodies as we get older that make us what we perceive as older. There's a biology there. And that biology puts you at risk for all of these different chronic diseases. So you could try to treat or prevent all of these individually, but if you're not affecting the aging that's driving all of them, there's a limit to how far you can go with that or how effective it's going to be. You prevent diabetes, but you get cancer. You cure Alzheimer's disease, which would be amazing, but then you have a stroke. But if you can intervene on the aging that's behind all of this, then maybe you can slow or delay or prevent all of these together. That's the great hope of geroscience.
So is delay or prevent aging? So earlier you said that it's not so much about living longer as it is improving healthy years of life. But what you just said was delay or prevent aging. So I'm a little lost there. Can you help me out?
Oh, delay or prevents all of the diseases and conditions that are driven by aging. So targeting aging as the underlying biology that causes or contributes to diabetes and dementia and cancer and heart disease and all of that. All of that might wind up helping you live longer. Who knows? But that's not the goal. The goal is to be healthier for longer, so that we all can spend more years independent and being able to do the things we want to do and in a state of better health.
So it's like the principle of the double effect. For those palliative care listeners, right? The primary, right? We're relating this subject to you. The primary intended target, in the principle of double effect in palliative care is often, opioids for pain relief. Mm-hmm. And yet as a secondary effect, if the patient dies sooner, that's acceptable. Your primary intended effect is to treat the diseases that are associated with aging, the conditions that are associated with aging. And as a secondary effect, if people end up living longer, then that's fine too. But it's not the primary target of geroscience?
I love that analogy. Living longer may wind up being a side effect of being healthier longer. But when you talk about, so aging is a weird subject, right? Because it's not a disease. It's not a bad thing. There are many positive elements of aging. I am happier now than I was 20 years ago. Hopefully I'll be even happier 20 years from now, even if I can't jump as high. So aging is not a disease. It's not a bad thing. And yet we're trying to target it, almost to treat it. So the goal is if we can slow or reduce the bad aspects of aging, the parts of aging that give rise to chronic disease, and you're living healthier longer, you'll probably live longer too in good health. Mm-hmm. When I go to a room and I ask people, so we're talking about aging as a target for therapies, who wants to live to be 200? And not a whole lot of people raise their hands because most of them are thinking, I'm not sure how I'm going to feel when I'm 95 or 85 or 75. And you extrapolate that out, and what am I going to feel like when I'm 200?
Right.
That doesn't seem like a great choice. But if you ask people, what if you could have the health that you have now, or the health that you had when you're 60, or the health you had when you're 50, and just keep that for longer? Most people would volunteer for that.
Interesting. So, Eric, go ahead.
I just want to make sure that when I hear aging, I think probably the common definition is I'm getting older. Like when you hear the word aging or use, what do you mean by aging? Especially as we're targeting aging. Like I can't target the clock. I guess I can target my clock and just turn it around. But what do you mean when you say aging?
Well, here's the geriatrician's perspective. So how do we know what old is, what an older adult is? For making a clinical decision, for example.
Yeah.
For thinking about prognosis, for example. There's someone I know who's done a lot of work around prognosis and how to estimate someone's life expectancy.
I don't know what you're talking about.
The name. It's around the tip of my tongue. So how do we know? And of course we know that, someone's birthday doesn't really help a whole lot with that stuff. There's 85-year-olds who are very fit and active and healthy and young. Mm-hmm. And there are 85-year-olds who are not very young. And what makes that difference? In geriatrics, we think of things like functional assessments, mobility and ADL function, IDL function, frailty, trying to get at that certain aspect of what does it mean to be older, to have an advanced stage of aging. So geroscience and aging biology is sort of the molecular reflection of that. So if we know that you have two 85-year-olds and one of them needs help with ADLs, they're going to be at risk for complications from surgery. But not necessarily because they need help with ADLs, but because that reflects their biology, the stage of their aging.
Right.
And we're learning more and more about what that biology really is.
Right.
Is it their telomeres, for example, like Eric said earlier, or how many senescent cells they have in their body, or what is their NAD reserve? What is the state of their chronic inflammation? How are their proteins folding? What is their proteostatic resilience? So we're getting closer to be able to understand what all of these biological aspects are. So we can look at someone who we think, is this person an old 85-year-old or a young 85-year-old, and know what their biology tells us.
I don't want to belabor this point, but I know some of our listeners are probably skeptics. We had one skeptic, a nurse practitioner on our hospice and palliative care service, Patrice Villars. We talked, we mentioned we were doing this podcast, and she said, is it something along the lines of, is it morally responsible to focus on helping people to live longer, given the current burden of climate change that humans are placing on the planet currently, much less if we were to live longer lives?
I love that question. And I love aging is a really unusual field to study because it's not a disease. It's something universal that happens to all of us. And that does make it a little bit different and opens up these really interesting questions about not only how to study it and what our goals should be, but also how to kind of, if we have therapies that effectively target mechanisms of aging, who gets them? How do we decide how to use them? How do we decide who should have them and who doesn't get them? And is that different from the way that we decide who gets other treatments? And these are really interesting questions.
In the work that you do, I'm guessing, because I think this is a really fascinating thing too, like if you extend life even 20 years, the ethical issues that come up, and even from a population density standpoint, can our Earth even handle that? And then who gets all these treatments? In the field of geroscience, are there ethicists in that field too that are looking at these questions?
Yeah, so this is a brand new field, an emerging field, and there are ethicists who are particularly thinking about these questions. Not very many, in the same way there's not very many clinician scientists who are helping to develop and study these therapies. But there are people who are just starting to really think about, because these questions, even 5 years ago, this would have felt like a really academic, philosophical kind of discussion. Therapies that target aging. Sure, let's maybe 10 years, 20 years down the line. But the crazy thing is the first clinical trial that takes a drug, in this case, that targets a cellular mechanism of aging was given to older adults to treat a chronic syndrome of aging. That first clinical trial has already been done.
What are they doing?
So this was a drug that targets protein quality control. It's a drug called rapamycin, and it's related drugs. And we can talk about kind of how this fits into the bigger scheme of mechanisms of aging. But it helps to activate pathways in your cells that kind of clean up misfolded proteins and help your cells to make fresh proteins that are more functional. So this drug and a related drug were first given to older adults before flu vaccine to see if it would improve the response to the flu vaccine. And it did. And then the next step, they did a clinical trial where they treated people with these drugs for just a month and then gave them a flu vaccine and saw that improved the response to a flu vaccine. But then over the next 6 months, they saw how often they got respiratory or other infections. And what they actually found was that the people who received this treatment just for a month had about a third fewer infections over the next 6 months. So it had this really interesting, long-lasting effect on their immune function in these older adults. So it was helping to ameliorate what we call immunosenescence, the decline in function of our immune systems as we get older. So it's a really small, limited thing. One drug, some older people, flu vaccine. It was just looking at infections. Doesn't seem like a big deal, and it's not. Except it was the first randomized controlled trial of a drug like this that targets mechanisms of aging in older adults to improve syndromes of older adults.
And it's already happened.
And it's already happened.
And I guess that's probably the hard part with this is that, like, I would imagine you can't do a randomized controlled trial with this drug for 20-year-olds and wait 90 years to see what happens to them, and then market that drug after 100 years.
Exactly. I mean, hey, the average RO1 lasts for 5 years.
You need results quick.
You need results quick.
RO1, for our listeners who don't know, that's the big NIH research grant.
So how do you study? Well, let me back up a sec. Many of your listeners, it probably sounds like crazy that we're even talking about studying aging in the laboratory. Like, is this really a thing we can do?
Right.
And the answer is yes. We've been studying aging as a process, as a biological process in the laboratory for decades now. And using the whole panoply of modern science to do that, from using model organisms where we can manipulate their genes and look for genes that control different processes, and high throughput drug screening, and using preclinical models like rodents and even primates. So we've been studying aging in the laboratory for a long time, and that's helped to give us a good sense of what is the biology that happens, what are the pathways, what are the genes, and figuring out in the laboratory at least how to change these things, how to change the genes, or how to give drugs that target the pathways to broadly affect aging. So we're already studying aging as a scientific target. But then the next step is, you have some stuff that looks interesting in the lab. Who cares? We can make mice live twice as long. We can, help monkeys and non-human primates to be healthier for longer. We can make worms live like 4 times as long. It's amazing what we can do with worms.
It's an old worm.
It's like 4 days.
Well, so worms actually live about, the worms that we use as the laboratory model, which is a little tiny roundworm called C. elegans. It lives for about 3 weeks normally.
3 weeks.
But you can make it live for 3 months.
Wow.
By just changing 1 or 2 of its genes. It's incredible. Even more incredible. So, hey, what do worms matter? I'm sort of a worm, but I'm not entirely a worm. You know what the very first, a researcher here at UCSF named Cynthia Kenyon, when she was at UCSF a couple of decades ago, was the first person to set out to find genes that regulate aging. So she decided to use the worm as a model organism, because you can do very powerful genetics with worms, to look for genes that control worm aging. And what do you think she found? What do you think was the first gene, actually, the first hit? And it turns out that this is still the gene that has the biggest impact on a worm's life.
I'm going to pass this question to Alex.
I was thinking of something snarky to say, but I have no idea.
It's the apple sensing gene, or what do worms like to eat? But no,
right.
So the first gene found in a worm, remember, that regulates aging, is the worm version of the insulin receptor.
Oh.
So it turns out that worms have fewer genes than we do. They have the same receptor for their version of insulin and insulin-like growth factor, IGF. But it's the worm insulin receptor that is still the single gene that has the biggest impact on a worm's lifespan and a worm's health as it gets older. And it turns out all the genes in the insulin pathway have huge effects on worm health and worm lifespan.
So, I mean, is it just because we're making diabetic worms who just die from hyper? Like, how do you tease out like okay, if I create something that kills worms because they become, I don't know if worms become hyperglycemic, but let's just say that. Is that an aging related issue, or did I just create this new acute to chronic condition that's going to kill them?
So we have some reasonable idea how this works in worms because you can swap
them
genes
out.
around in worms and
Chat with
cool
them.
stuff. Chat with them, talk about their goals in life and that sort of thing. So the way this mostly works has nothing to do with glucose regulation. It's metabolism linked, but it's not about hyperglycemia. It's actually about stress response. So worms with less insulin signaling. I'm calling it insulin, but it's the worm insulin IGF pathway. With less activity through that pathway, worms are more resilient to all sorts of stresses. So they turn on all these genes that help them to repair their DNA and repair their protein, and they go through life in better shape from when they're young all the way up to when they're old. So it's not about the glucose control, but it's about this receptor as a trigger for all of these stress response genes. And it turns out we have very similar genes. And it's kind of interesting that in worms this insulin IGF pathway is so important, and we can see this in mice too, in mammals. That if you change how they signal through IGF especially, but also through the insulin pathways, you can affect these stress response genes, these repair genes, and either make mice live longer or shorter. The analog with humans, so there's a group in New York and Albert Einstein who studies centenarians, humans who live in reasonably good health into their late 90s and hundreds. They've been looking for the longevity gene. What's the secret? What do these folks have that makes them healthy to 100? And we know pretty well now it's not one thing. There's no one gene that controls our lifespan.
Right.
But when they look for patterns, the strongest pattern they see is that these centenarians all have some sort of change in their own insulin and IGF signaling pathways, just like the worms did, and probably doing the same thing. Oh, talking about dual target effects, Alex. So affecting their glucose metabolism, sure, but also affecting their stress response genes and how they can keep their proteins repaired and their DNA repaired.
Do centenarians beget centenarians? Like, is it if I live to 100, my kids are likely to live to 100? I can imagine there's also like all these social determinants of health that also influence that.
Right.
Yeah.
Is there a connection there? Like,
there is. So there's a lot of discussion about how much of longevity is genetic, and I think the best answer is some of it, yeah. Probably less than we think, because probably a lot of that is confounded by the social determinants of health, which are huge in determining how you age. But there's definitely a genetic component to it too, and we know that somewhat from twin studies, for example. There's definitely no aging gene, but it does seem like there are patterns in genes that can be inherited. That can help some people. Some people win the genetic lottery, and it will help them to age in a more healthy way, and other people have different genes.
And you mentioned earlier there are some people. You mentioned who is going to have access to these treatments and medications, and this is a very important question. Think about there's some money flowing into this field, right? Isn't Larry Page? Didn't he start a company? Something about this?
For example, there's a company called Calico, which is not part of Google, but which is related to some of the founders of Google, who are very interested in this idea of therapies that target aging. There's a lot of interest in this field. I mean, aging attracts all sorts of folks.
Right.
It certainly attracts folks who want to live forever or want to try to find that secret to stay young forever.
Right.
But there's also a lot of folks who are in it to try to help the complex and sometimes intractable problems of aging that we see, and just give us better tools to do that with.
Right.
It attracts all sorts of folks.
Right. So there is a concern here about who will these treatments go toward, and with many other treatments in medicine, we've seen them go towards the best off groups, worsening disparities rather than
exactly
addressing them. So I imagine there's a similar concern here.
Absolutely.
Yeah. And I also wanted to sort of touch on what is not geroscience and ask you if you could talk, because, for years, decades, centuries, there have been people who have been purporting, this, that, and the other that treats aging, this anti-aging, that anti-aging. Is that all geroscience, or is there some line you'd like to draw on the field to keep some things out?
Is Dr. Oz a geroscientist?
Oh no! Don't ask me about Dr. Oz. and don't Google anti-aging. or search for that on Amazon. I mean, so Geroscience and the community of physicians and researchers and clinician scientists who are trying to create this field. The whole idea of geroscience is evidence-based medicine. So we think we have real biology, and we can show this in the laboratory, real biology that affects fundamentally the processes that drive aging. And I'm being kind of careful not to say, we're not trying to cure aging. Aging isn't something that we can cure or make go away or stop. And I don't even like to say we're treating aging, but we're treating the mechanisms that drive aging, the mechanisms that create what we see in each other as getting older. But the whole idea of geroscience is turning this into from a really kind of flashy maybe, but weird, philosophical, controversial field, and just turning it into another boring area of medicine where we're cranking out ideas, we're creating potential therapies and drugs and other things. We're testing them in clinical trials for outcomes that matter to people, and we're finding some things, hopefully in the end, that help to improve people's lives. So the whole idea is this is grounded in old-fashioned, data-driven, RCT-validated medical science. So what do we know right now for how you can cure your aging? Nothing. Well, I shouldn't say nothing. We know that, for example, exercise is amazing. And you can even cite plenty of randomized controlled trials for the benefits of exercise. And we know that intersects with the biology we're talking about, the biology of aging. I mean, exercise and activity are amazing. If you want to try to, improve your autophagy and your telomeres and your senescent cells and everything, exercise is the best way the best evidence-based way we know to do all that right now.
And how about diet? Mice fed fewer calories live longer than mice fed a regular mouse diet, right?
Yeah. This is fascinating, and this is the other kind of undergirding pillar of the science of aging. This goes back almost 100 years now. So one of the very first experiments that tried to make animals live longer in the kind of modern age of science involved feeding rats less food and seeing that they actually lived longer the less they ate, up to a certain point where they actually starved, and then they died. But as long as you don't hit that point,
right?
You feed them less and they live longer. And those experiments were done in the 1930s. And a lot of the field of aging biology has been trying to understand why that is. And we know a lot about that now. We know it's not actually about eating. It's not about how much you eat or what you eat. These are ways that you or I can kind of influence the biology, but that's not why they have biological effects. It's because of this close relationship in our cells and in all organisms between nutrition and mechanisms of aging and repair. So eating less or feeding rats less food or fasting, the kind of idea behind all of this is that these are sensed in your cells as there's less energy around, there's less stuff around. And all of our cells all the time have to make this choice between if there's a lot of energy around, a lot of nutrients, I want to grow and I want to divide and I want there to be more of me. I want to reproduce. And if there's not a lot of nutrition around, those cells kind of hunker down and they just want to survive. So the best way to do that is to turn on repair, to keep what you have in good shape. So fasting or feeding rats less food or feeding a worm less food, these are ways to activate these repair mechanisms in cells. But now we know what these mechanisms are. We know the genes and the pathways and the proteins that are actually involved. And we can, for example, design drugs to target these mechanisms directly. So that gets back to, remember I talked about what we're going to remember in history is the first geroscience clinical trial using a drug called rapamycin and another drug like it. So these are protein sensors. They actually affect the genes in our cells that sense how much protein is around. So if there's a lot of protein in food, this protein complex senses there's a ton of protein around. I should build stuff. I should build muscle. If there's not a lot of protein around, then this complex turns off and it tries to repair what you have instead. Rapamycin kind of short circuits that. It tricks the cell into thinking that there's not a lot of protein around. I need to really focus on preserving what I have.
Right.
And so it helps to keep your proteins in good shape. It turns out that's better for aging. Like there are times when we need to grow and we need to get bigger. So this protein sensor, which is called TOR, targeted rapamycin, if you want to put on muscle mass after you exercise, or if you want your patient who's rehabbing in a nursing home to rebuild their muscle strength after a surgery,
Right.
they need to eat protein and activate this TOR complex to turn on muscle synthesis. But you don't want that all the time. Most of the time, you want to repair what you have.
Right.
So a drug like rapamycin kind of gets right in there and turns on the repair mechanisms.
Right.
And that helps to keep an organism and keep cells healthier as they get older.
Is there an issue here with developing drugs to help humans deal with issues that we should be attending to using lifestyle modification, exercise, changes in diet, etc.?
I love that question. So that's also a question we get often asked. If so much of what we study at the molecular level in the aging field has to do with nutrition and exercise, which much of it does, much of it is linked. So why can't we just have everyone live the perfect life? You know,
or have healthy access to healthy foods in those food deserts throughout the world, or for those who don't have access to food.
So I think of this as in a couple of angles, right? So one is, when's the last time you guys prescribed an antihypertensive or metformin or aspirin or a beta blocker for someone with coronary disease or diabetes? I mean, there are many. This is kind of one of the things that we all have to grapple with in our society. Many of our chronic diseases of aging are at least exacerbated by environmental factors and the lifestyle factors related to that. But we generally don't hesitate to, sure, we would rather that someone be more active and kind of get the most benefit they can out of these lifestyle changes. But we also use drugs. And we don't generally hesitate to do that because, you certainly don't want to let someone stay hypertensive while they're trying to lose weight. So we do both. But I think, that there's always going to be a role for pharmacological therapy to kind of augment lifestyle changes. But then there's the other kind of issues that not everyone gets the same biological response even to activity or exercise or fasting. Right. So it may work for some people, but not others. And then, you and I, we all know that this stuff is not determined by like willpower or by, gumption or whatever. They're real barriers, including many of the things we refer to as social determinants of health, which can prevent people from being able to live a healthier lifestyle. And I think that understanding how that affects them biologically can hopefully help us as a society to change things, to make it easier for people to eat real food, and to live a more active lifestyle. But still, there's always going to be people that just aren't able to do that and need some help.
Right.
You mentioned metformin. That's also a drug, right? That
heard of that one?
Yeah, that has something to do with I won't say anti-aging. Geroscience.
It does. So the perspective of a geroscientist is that metformin is a drug that affects mechanisms of aging and lowers blood sugar as a side effect.
How does it do that? How could it do it?
So metformin is, so believe it or not, even though we've been using metformin for decades and millions of people take it, and we have all of this data about how it affects people's health, often in a good way, especially with diabetes, we still don't really know exactly how it works. We have a few ideas. It may be more than one thing. But several of the things we know are that it kind of gets into the same idea of nutrient sensing. So metformin helps to trick your cells into thinking that there is not a lot of energy around and not a lot of sugar around. And so it helps to make your cells more sensitive to the energy and sugar that's there. It also probably activates some of the same protein quality control pathways that rapamycin does. And there's some evidence that it works in mitochondria for the same thing. So kind of optimizing how your cell uses energy and helping to turn on some of these repair pathways that are affected by energy and metabolism. So it turns out a side effect of that is that metformin sensitizes your body to insulin and lowers blood sugar. And that always gets me back thinking to those worms, right, with their insulin IGF receptor and how important we know that insulin signaling is to health and longevity in general. Metformin seems to be one of these drugs that gets at that mysterious root biological problem of diabetes, the idea of insulin resistance and metabolic dysfunction that we still don't entirely understand, but which I think is pretty closely related to mechanisms of aging.
Okay. So I guess the question I got is, like, we're developing these drugs, but it also seems like we've had millions to billions of years to, I guess not billion, but like to evolve and to develop all these mechanisms that if we take something, there's always going to be a side effect. And even in those worms that you talked about earlier, it sounds like there's got to be a trade-off, right? There's a reason why they only live 3 weeks versus 12 weeks.
Yeah.
Is there a reason? Like, why didn't evolution build 12-week living worms instead of 3-week living worms?
We should ask the worms.
I've tried. Birds keep on eating them.
Well, so one thing we know is that there's no perfect genome, there's no perfect diet, there's no perfect lifestyle. Nothing is always good. Everything has its own context, right?
Yeah.
And what we're talking about with protein sensing, this is my favorite example of this. Like in general, for most of your life, you would rather be repairing your own proteins than building new ones. And in the laboratory in animals, we know that doing that helps to prevent metabolic disease in animals, helps them live longer. But there are times when you actually need to build muscle. So there's a time and a context for everything. Oh, there's a song about that, isn't there, Alex? There's a right time and a right context for everything. And evolution may have optimized us for a certain environment, but our environments are different now, and what we may need from our bodies at different times may be different now. And we're starting to learn how we might be able to help our bodies to do that.
So I have two more questions. One is, talked about a lot of treatments that are effective in rats and mice and worms in a clinical trial in humans. Are there any treatments out there that are closer to being ready for prime time in humans?
There's a bunch of treatments which are in clinical trials now. And we should talk a little bit about this. How do you test something that you think affects aging broadly, right? So Eric was suggesting that we run an 80-year clinical trial. We enroll college students.
20-year-olds.
Randomize them.
That way they've built up their muscle. We're in repair phase now.
Exactly.
Instead of building phase.
Yeah.
See, I'm learning something, John.
There we go.
Watch them for 80 years.
So how would you design a clinical trial?
Yeah.
And there's a lot of folks a lot smarter than me who have been trying to think about this. Many of them are geriatricians. And if you want to test whether something broadly affects aging, then you want to look at outcomes that broadly represent aging. So what do we think of as, what are the, sorry, I'm a scientist. What are the phenotypes? What are the conditions or the syndromes that we think of as most representative of aging as a whole?
Frailty, multimorbidity, cognitive impairment, disability. Mm-hmm.
Yeah, functional status, ADLs. Yeah, exactly.
Hearing, vision.
So one of the ideas is using these sorts of complex syndromes, complex multifactorial syndromes, which represent aging, using them as outcomes in clinical trials. So that actually is, it might be an effective way to run a clinical trial, because you could really see if you affect something like frailty in just a couple of years, or something like multimorbidity, as we'll talk about. But it also makes sense biologically. So what is a geriatric syndrome? Geriatric syndrome it's a common phenotype, something like a fall, or like delirium or dementia or cognitive decline, which has many causes. They're multifactorial. They're caused by problems or changes in a bunch of different organs, a bunch of different tissues. And how do we treat these things as geriatricians? We try to identify all of the underlying contributors we can. Like, how do we prevent delirium in the hospital? We try to treat all of the things we can think of that might be contributing to delirium. So we try to address all of the multifactorial issues. So maybe we can do that biologically too. If you have a therapy that targets aging mechanisms, that, for example, helps to improve your protein homeostasis, that's not just good for. So proteins misfold in Alzheimer's disease, right?
Right.
But they also misfold in your heart, and they misfold in your kidneys. They misfold in your pancreas. So something like a fundamental process like protein misfolding affects lots of different tissues.
Yeah.
And so maybe if you're trying to help a complex multifactorial syndrome, maybe you need to use a treatment that could address or help a bunch of those contributors all at once. So that's the idea. Use therapies that target aging mechanisms, and then geriatric outcomes, things like frailty,
right,
ADL function as outcomes in a clinical trial.
Right. So are there any current treatments or medications that are in testing?
So one group are these protein sensors. They're rapamycin and similar drugs. Another drug in testing, if not right now, soon, is actually metformin. So the idea is that if older adults, so this is called the Targeting Aging with Metformin study, which hopefully will be getting underway soon if it's not already underway. And it's going to use multimorbidity as an outcome. So the idea that metformin doesn't just affect diabetes, but it might, this is what they're going to test, it might slow the onset of other chronic diseases like cardiovascular disease, which we already have a good hint it does, or dementia, or cancers. So older adults will take metformin for several years, older adults who are already at risk for multimorbidity, and then they'll follow and test whether metformin slows the onset of multimorbidity.
So the trials, are there some things that we should just be recommending that right now that targets? It sounds like exercise.
Absolutely exercise. No dose too small, never too old.
Never too old. Diet, do we have any firm recommendations on diet? Ketogenic, intermittent fasting, just eat healthy?
What does eat healthy mean?
Everything in moderation, including moderation. That's my own feeling. Like,
I like that.
Try to eat. What was it?
Mark Twain one-upping the Buddha.
Yeah. What's that? More greens, less meat. Isn't there a quote from?
Eat plants.
Eat plants.
No, eat food, mostly plants, not too much. Yeah.
Yeah. That seems like that to me is the epitome of a healthy diet right there.
That's good. I think that's good general advice. Diet's not a controversial field at all. It doesn't evoke passions in anybody.
There's no money
boring.
in it either. So
no, none at all. I've never seen a book suggesting what diet people should eat.
Never.
There's a lot of talk about intermittent fasting.
There is. And this is also a subject actually of clinical trials. So there is a large randomized controlled trial that's finishing up now that took healthy middle-aged adults, not obese, healthy, and put them on a dietary restriction regimen. So just like some scientists did with the rats 80 years ago, to see what effect it had on the health of or already healthy non-obese middle-aged adults. So we're starting to study some of these diet things in clinical trials. There's a few interesting studies about using ketogenic diet in certain dementias. There's some interesting studies about different fasting regimens in metabolic disease and diabetes especially. Outside of the diabetes world and the weight loss kind of world, there's not a whole lot of data yet on how these might be useful. They might be. But the thing about diets is that everyone responds so differently to different foods and different diets. It's hard to imagine that a diet intervention, even something like fasting, is going to become the sort of thing that you could just prescribe in the same way that you would prescribe a drug for a condition. But one of the interesting frontiers is if you can figure out who might get certain health benefits from different patterns of eating, which we're really bad at right now, then maybe that could become a useful tool.
Personalized diets. So
still a ways off.
Last question for me. You had a terrific article about much of what we talked about. You were an author on this paper in Nature, which is a amazingly prestigious journal. Congratulations.
Nice.
And you also authored a paper in JAGS about the need to improve the pipeline of researchers with an accompanying editorial by Tom Gill. Is there anything you want to say to encourage any of our listeners to go into this field, or to convince others that, hey, this is a thing? We need to get people in our group who are working on geroscience.
Well, I think that geriatrics is the most exciting and fascinating and rewarding field of medicine. So if you're a medical student, if you're going to medical school, if you're a resident, hey, talk to some geriatricians. It's amazing work, and I love being able to help people so profoundly, often with such simple things. And And I guess all that I would say is that geriatrics is already an amazing field, but it's getting even better because it's becoming a translational field too. It's becoming a field where we can add our understanding of the biology to our fantastic clinical care programs. And we're going to have better, new tools, different tools that we can add to the tools we already have to try to help keep our older adults independent and healthy for longer. And that's my goal. So what I mostly do in the clinic, I mostly work in the hospital. I spend a lot of time trying to prevent delirium and trying to prevent functional decline and helping people to get home after the hospitalization and staying independent. And, we have some amazing tools and care programs to help do that. It's amazing how important getting out of bed is, just getting out of bed and figuring out how to do that. And, keeping the shades open and keeping people's circadian patterns in sync while they're in the hospital. But I would love to have better tools too, because even when we do the best we possibly can, there are still people who get delirious, and there are still people who lose their muscle strength and can't walk and wind up having to, go to rehab, go to a nursing home, and maybe not get home at all. And I want better tools to help those people. And those tools are coming. So if you think that geriatrics is a cool field, if you want to do amazing science that uses the biology of aging to try to help people live better lives longer, stay independent longer, I think this is an amazing field to be in for the next couple of decades.
I'm sold. Sign me up.
Career change. From podcaster, clinician, educator to geroscientist.
I will get you guys your pipette men. We'll do our first Western blot tomorrow. It's going to be fun.
I'm going to find some worms in my garden. John, thank you very much for joining us today. Alex, can you maybe end with a little bit more Queen?
Maybe we should say not who wants to live forever, who wants more health span. It doesn't have the same ring to it.
No. We can't do that.
Compression of morbidity.
There's no chance for us. It's all decided for us. This world has only one sweet moment set aside for us. Who wants to live forever? When love must die. Oh, sorry. That's kind of sad. That's part of the song.
Well, John, very big thank you. And for our listeners, we will have links to the Nature article and the JAGS article and accompanying editorial on our show notes on the GeriPal website. We are requesting a special request to all our listeners. Our 100th episode is coming out. So please call 926-GeriPal. Yes, we have our own phone number now. And leave a comment of one thing you liked about one of our show episodes or anything about our show episodes, 15 seconds or less. And hopefully you will be on our 100th episode podcast. So take that little moment. Really appreciate you joining us today.
Thanks, folks.
Guys.
Thanks, John. Bye.